that would be great. And now we invite Vlasta, who is going to be introduced by Dr. Mershon.
Thank you for introducing the introducer. So it is my great big pleasure, come around, to introduce Vlasta Kubusova. She is a MISTI scholar, and she won a grant to come here to MIT and work with us on sensible biomaterials. And her work combines three-dimensional objects, colors, scents, synthetic biology, cell-free expression kits, olfaction, colorimetry, and you name it. This is the quintessential Media Lab approach. Put everything in and then see what wonders can happen. Please, take it away.
Thank you very much for this nice introduction. So it's a little bit moved down, but I hope it's fine. So thank you, Andreas. So I'm the PhD candidate at Slovak University of Technology, now currently working with Andreas and other people as MISTI scholar at MIT Media Lab, but I'm also co-founder of Crafting Plastic Studio, which is a design research studio in Slovakia, where we explore different bioplastic for value-added products. But today I would like to introduce you to SenseBiome, which is a project where we explore the possibility of creating interactive and responsive biological materials by using synthetic biology methods. So this is the incredible team behind that's composed of designers, bioengineers, olfactory experts, and architects. And the project started last year when I came to UPenn to Dumo Lab as a Fulbright scholar. So materials are in general mostly perceived by their visual aesthetic and tactility. The olfactory context is very much less present. However, it plays a crucial role, for instance, by identification of the origin of the material. The olfaction also influences our experience in the room, our interaction with the space, and also the interaction with other human or non-human habitats in the space. But olfaction also unconsciously influences our behavior and mood. So the question is if we would experience the space differently when the olfaction would play a big role in it. So this project on the screen was a starting point for me when I really started to get excited about olfaction systems. It's a project by our studio and German architectural office MMK, in which we used the GCMS analysis method to analyze and recreate the smell of primary resources from which we produce our bioplastic composites. We did it in order to create an additional identity for bioplastics, since visually it's almost impossible to distinguish them from oil-based plastics. And this lack of identification within bioplastic industry starts to be quite a big problem for customers, but also, for instance, for a waste management industry. However, this was quite a static solution, and in this project, we started to think a little bit farther, and we wanted to imagine what if we could create materials that are more dynamic and responsive. Are we able to create materials with the new olfactory and interactive features to help us make our room healthier, to possibly identify the potential threats, maybe to help us react to our moods, or even help us to reduce the stress? So we think yes, and we also think that we might achieve this through the intersection of these three things, which is synthetic biology, biofabrication, and biologically driven materials. So Sensible Matter, or SenseBiome project aims to develop and scale these new sensible and responsive biocomposites for product and architectural use. As a first prototype, we decided to work and develop a biomaterial-driven and computer-controlled manufacturing of aroma-active lattices. So we work with biomaterials and polymers, which are mostly used in medical application, and their use in durable consumer products for day-to-day application is quite novel and not fully explored yet. So biologically driven materials are excellent candidates to enhance the interactivity thanks to their programmable properties. These plants that we are working with, for instance, include silk fibroin or other materials that could potentially also preserve the smell longer. At the beginning, we started exploring the integration of living bacteria to our material blends for 3D printing, but since working with living matter brings with it many disadvantages, such as the need of keeping the bacteria alive, the potential contamination, and many more, we decided to work with another option, and that's the cell-free expression system. So this system has a great advantage because it offers a living-like approach while having all the machinery to produce protein from DNA without having all the actual living system around. And we use the cell-free system to bridge the scale of DNA design to material substrates for their expression, activation, and interactivity. So we produce our lattices by using blends that are 3D printed with water-based 2.5 printer for large-scale fabrication. These blends and hydrogels are therefore printed layer by layer, then dry and later fold into lattices. We created this cellular pattern to enable the integration of freeze-dried sample into separate lattice system. So we are working on different genetic circuits encoded in DNA or NAN or RNA. We construct plasmids that contain our desired interactivity and add them to cell-free reaction. So this is an ongoing project, so we try to work with different color, protein, and enzyme expression and enzymes to later add the biomaterial into them, and then freeze dry the materials, cut it into pieces, and later let it rehydrate and activate by either water or substrates. In the future, hopefully in the near future, we would like to also try to express different olfactory receptors to possibly detect various other molecules. So we are now doing a very small steps towards this new dynamic matter, which could adapt, interact with us, and maybe be responsive to its environment. We envision the future of healthier materials that could inform us about the invisible threats, gases, airborne pollutants, help us to balance our stress level by releasing customized smells, maybe attract or navigate insects, or inform us about the air quality and potentially release air-clearing substances. This is a visualization of the installation that we will have next week in Philadelphia at the Institute of Contemporary Arts, where where you are all invited to come. And in this particular installation, we will work with singular molecule with the air clearing capacity. So I would like to thank you again to all this team and the ongoing support from Laia Moga-Soltevila from UPenn and Katia Zolotowski from RISD, and of course Andreas Merschin from MIT. And since you can see that this is very ambitious project, we also hope that through this conference we might find maybe possible collaborators for future. So please let me know if you are interested. Thank you.
Yes. So, thank you for this, Vlasta. I have the first question. I am so happy that we have Aromics in the room. We have Adam Feldman in the room, who's a prostate cancer urologist, amongst other things, and also a co-founder of a startup that wants to sniff prostate cancer from urine. And we have Vlasta in the room, who wants to put olfactory receptors into objects that you can just hold. No longer is it going to be a liquid. So I was wondering, does the future mean that we can have your objects maybe as part of a booth that you walk through, and it smells you and it tells you, it lights up with where your cancer is? If it lights down here, then it's the prostate. If it lights up here, it's the breast. Or other things like this. Assume success. Assume we can do this. Where would you put these things? What kind of applications can you think? You listed so many about mood and health. I want to see what else can you imagine that your materials can do, assuming that they work. And eventually we'll make them work.
So since we started this project with the architects, we are really thinking about the application within the rooms, so somewhere where we can possibly experience the smell or the scent very intensively or more intensively than outside. But we were even thinking of different applications for insects and pollutants outside in exteriors, when it's maybe not related to humans at all, but rather help to maybe navigate them to the place where they cannot come or should come, and so on. So this is one of the options. The other thing that I really like to think about, that's what we also discussed last time, is that this kind of system could enable us to really detect these invisible things that we cannot see. And by then we could maybe really understand or get the navigation, maybe the color navigation about the odors of the ripeness of the food, but also about the degradation level of different materials. So there are plenty of possibilities.
Yeah, I was just wondering, what is the lifespan of these materials?
So these particular materials that we are now working at Penn, that really differs on special blends. Since most of these materials are now being used in medical applications, they don't have quite a long lifespan. But this is also what we are now working on. So here, that you can touch later, this is made of our materials, which is made up of PHA-based bioplastics. And this has quite a long lifespan, up to several years. So I think there has to be find this kind of like a balance between the biopolymers that are using in chemical bioplastic blends and the biomaterials to make them durable and for long-lasting applications.
Thank you.
Unless there's questions from the internet, I have one last question.
And please feel free to touch this later.
Yes, and she has her email up there now, which is a very proud email. She got an MIT email. I'm very happy for that. Vlasta Kubusova at MIT, please send her emails and questions. I have a question for you, Vlasta. She said something very provocative to me. She said that her materials can help preserve the smell. Now, how important is that for, let's say, diagnostics? If we want to preserve the smell in urine that is telltale of a disease that we want to then present to a machine or a dog, or if we want to preserve historical smells, for the law, for instance. If somebody has I had actually this happened while I was a TA in my grad school years. I had to deal with this situation where one of my students had possibly some metabolic disease where his body odor was so intense, it would actually literally bring tears to the eyes of anybody sitting within maybe even 10 feet, even more. And when this, this poor person would sit in our giant, bullpen of graduate students where we had all our offices, we could not work there. There was 40 of us, and we all had to leave. So you have no idea how devastating that was to that person and to all of us. And I was having to parse questions such as, this other student is now complaining about their grade, and they're saying that the reason they did badly on the exam is because the smell was so intense. Well, this ends up being a legal issue at that point. So you can record, preserve the smell, and say, and I was on board with this. I was saying, look, we have to have some special accommodation because this person's body odor is just so offensive. It makes other people not able to concentrate. And this person, of course, was completely anosmic to their own body odor. So for them, it was a huge mystery. They were claiming racism. They were claiming all sorts of other things. And I was pointing to my eyeballs. I'm like, do you see my eyeballs watering here? This is what's going on. It's not your fault, but it's also not possible for me to sit here with watering eyeballs trying to tell my students that it's okay for you to do an exam. So preservation of smell has such a great big impact on everything. And it's so ephemeral. We can preserve sound, we can preserve light, we can't preserve smell yet. So your materials might end up being the solution to that. So unless there's more questions, let me introduce the next speaker. Thank you again.